Today, I want to talk much more about how can we anticipate problems and how can we mitigate problems. We already established that models make mistakes, and that's something that we fully can't avoid, right? Models will make mistakes, even the most accurate models. We might accept that, or we might want to try to do something about it so that a mistake doesn't affect the users. We see over and over again common excuses where people just say, well, it was a software mistake, nothing that we can do. Here's an example that we'll talk more about later of Apple support essentially just saying, oh, this discrimination in credit scores that we may have predicted, nothing we can do. It's just the algorithm. We're not trying to discriminate. But somebody has built the algorithm and somebody has not thought about those problems or mitigated those problems. Right? We see similar excuses. It's just data. Well, the model learned from biased data, but still we can do something about it. And as designers, as engineers, we may have some responsibilities to think through what we're actually building. At least that's what I'm trying to convince you throughout this course over and over again. We had this case of Thomas Midgley with two disastrous inventions, one of which he could have very easily anticipated that lead was a nerve toxin, right? And maybe we shouldn't have designed this. So the theme of today's lecture is if you do something dangerous, if you do something stupid, maybe think about what the mistakes are and plan for them and mitigate them. And this has two parts. We're covering both today, but in reverse order. First, you need to figure out what are the mistakes that we need to worry about, and then what can we do about them. We're starting with the second here, where I want to go through a couple of strategies that all come kind of different ideas of how we can deal with mistakes. How can we make sure that if a model makes a mistake, it doesn't turn into harms, or how can we at least reduce the harms, reduce the risks? I want to go through them one by one. The first is one that everybody keeps talking about, is putting humans in the loop. The idea is pretty much rather than fully automating a decision, you have a human there that may need to confirm actions, that may need to be reviewing certain steps before actions are taken. For today, I want to take an example of an autonomous train. Does anybody know where this picture is? This is London. This is a Docklands train in the east end of London and has been running without a driver autonomously since it was created in the late 80s. So autonomous trains are not necessarily something completely new. They are deployed in a lot of subway systems too, but it's something that's still not broadly deployed in all kinds of systems. And we have a number of requirements. And remember, these are requirements, things that should not happen in the real world or should happen in the real world. The train shall not collide with obstacles. The train shall not depart until all doors are closed. And the train shall not trap people between the doors. So we can think about machine learning components here that, for example, navigate the train, accelerate, stop the train, or that control the doors of the train, when to close, when not to close the doors, and when to depart. So if we want to assure these requirements, and we have a usually autonomous system, what are ways that we can put a human in the loop here to make sure that problems don't occur? And again, type to Slack. I think that's probably the easiest. I want to see, again, many people are typing. How can we assure those requirements that they are held with a human in the loop, even if the model occasionally makes mistakes? The model that detects people in the door or the model that detects obstacles. Still have a driver to supervise the train. Yes, that's one way, although a little bit counterproductive if you want to have an autonomous train. But you could certainly have somebody in there checking every action or being able to intervene or just controlling the doors. What are other ways of keeping a human in the loop? Yeah, remote operator. For example, for the doors, you could have one person overseeing many different trains to click a button when the doors are closed or to confirm what the model thinks that the doors are free of obstacles. Also, if the train is stopped, have a remote operator, like if it doesn't know about obstacles, there may be an obstacle, have a remote operator look at the video and control it remotely. Right? Video feed to see obstacles and approve. Probably you don't want to approve every time there is an obstacle before stopping the train, but you might correct if an obstacle was incorrectly detected. Right. The design process, there's, I think, at least three common approaches. You can think about the interaction between whether to have a human in the loop or not. You can automate a decision. For example, the train automates when to close a door, so you have no human in the loop. You can prompt, which means you ask for confirmation. The model makes a suggestion, but before an action is taken, a user has to confirm. For example, the train will say, I might want to close the doors now, but the remote operator has to confirm first. In organize, annotate, augment are different ways where information are just presented. You don't directly prompt something, and it's on the user to take action at some point. A spell checker is the most common example here, where it draws squiggly lines after misspelled words. And then it's on the user to either take a decision or not. With a train, you could do something similar where you say the doors are not informing you that the doors are now closed or there are obstacles, but you probably want something more forceful where a human actually makes decisions at specific points in time. The idea here is that humans and machine learning models are good at different predictions, different things. Humans often understand context better, but AI automation scales better. So you often want to find some combination. But there's actually lots of known challenges here of how to do effective oversight. Humans are pretty bad monitors. They're fatigued, they're complacent. There's lots of examples where humans just click away warnings and then bad things happen. These are common examples of how do you deal with unreliable models. So for example, suggestions for answers in Google Mail just make you suggestions. This is an annotation mode or an augmentation mode. There's no automated decision here. It's not a prompt. You either click the message or you don't. And even if you click it, you can edit in the next step. So the human is fully in control. It just supports a human. I think you may have talked about this example last week. Fall detection with a smartwatch. If you detect a fall, you might want to call the emergency responders completely automatically, but maybe you want to give the human a chance to detect false positives and cancel this before it's fully automated. So you have a time buffer there where a human can intervene. There's also lots of challenges of explaining humans when to trust a model and to not trust a model. And honestly, what we often need is to foster mistrust. Humans are often too trusting of a model here. So you actually want to calibrate this down. We will talk about some of this much later in the lecture. So there's lots of different designs with keeping the human in the loop, and we need to be careful that we're not getting rid of all the advantages of having automation in the first place, but it's a common strategy. Something that sometimes works is having the action that we automate be undoable. So if we do something, we can undo them later. The most common example here is probably a thermostat. If you don't like the temperature that it's setting to automatically, you can just turn it back to the original value. There's many other things where PowerPoint design suggestions, if you don't like it, there's an undo mechanisms. One-click shopping or a mechanism where it predicts what you like and it sends it to you automatically. With free returns, it's kind of an undo mechanism and so on. Yeah. Can you think of any examples for the train where you can undo something? the train runs fully into an obstacle, you can undo some damage, but probably that's quite expensive and not what you want. You can open a closed door again. Maybe you have some emergency override blocking the doors, right? So you can think of this as a design strategy, something that you can do in some cases with more effort, in some cases with less effort to undo previous actions. If the train recognizes braking, you can override this and get it running again, things like this, yes. Another common strategy is to provide guardrails. Guardrails are essentially general predictions on outputs of models. So you post-process the predictions of a model before you take actions. You have some way of truncating values that are unrealistic. You may know certain parts of the model that have low accuracy, spaces of the input space that may have low accuracy. So those kind of things, you could have some automatic mechanism to deal with. Before Twitter became pretty much useless, this word bothered association was one of my favorite Twitter accounts. It has lots of examples of often expensive German cars driving into bollards, protecting pedestrians or buildings. This is a good example of a guardrail. You have a part in the system that prevents larger damage by anticipating where mistakes happen and then just blocking those mistakes in some way. There's also lots of examples in hardware protections. So for example, if you have a smart toaster that you don't want to catch on fire, you could make the machine learning model much better to not produce too much toasting time. But a much simpler thing is, like in this picture here, there's a a very cheap device, a thermal fuse, which if it gets too hot, it just cuts out power in the system. So this is a guardrail here that makes sure that the toaster never gets too hot, independent of whatever predictions the model makes. Can you think of any guardrails for the autonomous train example? Again, write in Slack. Anything where you would mistrust the outputs, check the outputs in a uniform way, or any other design changes to minimize harms that certain things just can't happen. Speed limit is a good example, right? Whatever the model predicts, whatever speed it predicts, just cut it off at a certain maximum speed. You may have a map that certain corners can only be taken at a lower speed, whatever the model says. Any other suggestions? Door guardrails. So that's actually an example I have on the next slide here. Screen doors, platform screen doors are a good example of preventing people from falling onto the tracks. So fewer obstacles to recognize. The trains stop at very predictable places, screen doors open. Pretty much all these autonomous train systems are very clearly separated from other traffic too. So you have guardrails in a way that you don't have cars on the tracks. So all these kind of things are possible guardrails, and you can think about them in all kinds of machine learning systems too. A seemingly similar but somewhat different strategy is that you have a way to detect mistakes and recover from them. So often, this is traditionally known as a doer-checker pattern. The doer here is the original model that makes a decision, for example, to determine the speed of the train. And the checker model or the checker component is an independent component that has some way of deciding that the output of the original model was wrong. A classic example here is, again, the model that determines the speed of the train as a doer component. And then you have an independent thing that's not just another machine learning model, but for example, a gyro sensor that detects when a train is going around a corner too fast right? Because the g-forces become too high. In this case, you can just start detecting, oh, the train is going too fast around the corner, and the checker will start a recovery mechanism, braking in that case. There are all kinds of mechanisms of detecting sensor failures and also model failures with some kind of diagnostics. Let me skip those. But then when you detect a failure, you need to think about what are you doing now? In the train case, you brake. If you detect that the model makes a distinction, maybe you don't act on that distinction. Maybe you reopen the doors. Maybe you switch to manual mode. Maybe you just drive very slowly if you're unsure about the detection mechanisms. So the whole point of this thing is that you have a model that's quite different from the original model. And one place where you actually see this, and I was expecting a slide here, oh, it's in the wrong place, is LLM as a judge. You probably have seen this in some form where a model makes a prediction and LLM generates some text, and then you have again a model with a different prompt asking to evaluate that generated text. For example, you could ask, is this polite? Is this biased? What's the tone here? Is the sentiment okay? You could check for factualness. And the idea here is that the original prompt does something pretty complex, but then each separate check does something much, much simpler that's easier than generating all the things together. This is a pretty common strategy that we'll talk about in about a week for model evaluation that kind of has this idea of a separate checker. So you have the original Dua model that generates the text, and then you have these individual components, individual checkers for one small piece at a time. That's kind of a little bit redundant, but conceptually different enough that it has a decent chance of detecting problems in a somewhat independent way, in a somewhat more reliable way. And when you detect one of those problems, for example, this answer is not polite, then you can stop, regenerate, or run a second prompt, intervene, correct in some form. All right. I have two more, and I think they're pretty obvious. One is redundancy. So rather than just have one model predict how fast the train can go or whether you can close the doors of the train, have two models predicted and see whether they are consistent. We already do this with ensemble models very often. So if these models are very similar, there's often not a huge value in redundancy, I would say. Even if you train quite different models on the same data, they often learn similar mistakes. Redundancy works better if the models or the approaches are quite different. So maybe you have a visual way of detecting whether people are blocking the doors and maybe some LiDAR mechanism independently, so that you want to see whether quite different things work together. So sensor fusion is essentially that strategy where you look for multiple different things. It helps increase reliability and detect common mistakes. And again, some of these sensors can be, or some of these models can be rather for special purpose, very specific things. And the last one I want to talk about is containment and isolation. That's something that I think until a year ago, I would have said is not particularly useful in a machine learning context. The idea here is that if a component makes a mistake, you don't want that mistake to propagate. The traditional example is something like this here. This happened in a military ship where somebody entered an invalid value into a database. There was a divide by zero crash in the database. And when the database crashed, the entire network went down and the entire ship went down and was essentially dead in the water. This was not a action scenario where this was real danger, but it required rebooting the entire ship. And you wouldn't really want that somebody can enter invalid data and it takes down the entire ship. That seems very independent. So what you typically want in system design is handle mistakes as local as possible. Don't let them spread to other components. So machine learning models don't typically crash. This is not something that we usually worry about. So we don't really worry about the model crashing and taking down other components this way, but it may give an incorrect answer, and that incorrect answer can propagate in the rest of the system. It's hard to figure out how do you get low critical components in a model and not use it in a different setting. But one place where I think this has been coming up a lot very recently is with agents. When agents use tools, they delegate tasks to different tools. For example, you may have an agent that can get an email, send an email. And you might want to be careful that it doesn't get information from one data source and sends it to a different data source. So people start thinking much more about isolation here. Maybe you, instead of having an agent get an email and formulate the next email, you have some sort of sandbox where you do some local computations without access to the full context. You can have strategies where you have a step of computation with an LLM that generates a response. We had a sentiment analysis example in the past, and then you narrow it down to only possible values like positive, negative, or neutral sentiment, so that you can't really spread misinformation there. There's just three possible values here. Even if the model makes a mistake, it cannot start sending arbitrary different text. So I think there's not really clear designs here, but I think isolation makes some sort of comeback of maybe separating different part of a context of a model, giving models very selective subsets of context, and so on. So this is what I wanted to cover in this part. These are different strategies of if you anticipate a mistake, if you know the model might be unreliable, what can you do about it that it doesn't cause worse consequences? Right? We talked about human in the loop, usually having a human check before a decision is made. Undoable action, recover from a mistake, reset it to the original value. Guardrails, protect against model outputs being invalid or unreasonable in some way. Mistake recovery and detection and recovery have a way to independently detect problems and a way to recover from those. And then containment isolation, where you make things not spread very much. I want to do a breakout next, where I want you to apply these strategies. So before we get there, any questions about these? The lines are a little bit blurry sometimes. So undoable action has some human somewhat maybe making a decision to undo something, whereas human in the loop typically assumes that you review a decision before an action is made. Sometimes humans complain afterward. Guardrails usually don't rely on detection that much, but to some degree. It doesn't matter too much that you can clearly distinguish all of them in detail, but a rough distinction overview, I think, would be quite useful here. So what I want you to do is look at two separate scenarios. One is automatic audio captioning, so subtitles for streaming services. So think of Twitch or YouTube streaming, and you want to automatically generate subtitles. So you have mistakes in the model, you want to mitigate them somehow, maybe. And then the other thing is more complex. You have a calendar agent, a tool that whenever something changes in your calendar or whenever you notice, it monitors your phone location that you're running late, that you won't make a meeting, it will automatically try to reschedule meetings for you, where it might send some emails, access your calendar, and so on. So I want you to think about, for both of these, think about one harm for each. And then think at least which of these strategies, human in the loop, undoable action, guardrails, mistake detection and recovery, or containment and isolation might be useful to make this system work better and reduce the risk of those harms. Any questions? All right, we're going to put you into breakout groups. I want you to do the usual thing to post as a group in Slack and tag all other group members. Let's say about 8 minutes for these two.
Ready, set, go.
So we chatted about how we should volunteer somebody, but we figured maybe you can volunteer by raising your hand to talk about what you talked about in your group. Anybody willing to share?
Validate me because I am the one who suggested this and saved you all
Right.
from cold calling. Perfect.
Let's let's start with John.
Hi. So for the first application, we were like seeing different problems that there might be, like incorrect captions that can change the meaning of dialogue or spread misinformation. And we were talking about like different guardrails that could display confidence indicators and disable captions when confidence is extremely low, or
Okay.
even undoable actions like allow captions to be updated or corrected after publishing instead of being permanently fixed.
Okay.
Mm.
So the latter is maybe a little bit nitpicky, but if you're fixing things after the fact, it's not really undoing things, just correcting things. This might fit better in the kind of detection and recovery strategy. It doesn't matter too much where exactly it is, but technically undoing is reverting things to the original state. But yeah, you want to talk about the calendar agent too?
Yeah, so for that, there could be incorrect rescheduling due to bad predictions. So probably cancel important meetings
Yep.
unnecessarily or create a scheduling conflict. And for that, we were talking about the importance of always having a human in the loop, like a confirmation before rescheduling meetings, especially when other participants are involved, or even like and double actions as well. So provide a clear undo option that restores the original meeting.
Yeah.
I mean,
So
instantly. Yeah.
undoing makes sense. You can make it easy to undo. Can still be annoying, but yes. Um, Human in the loop in the kind of prompt sense, right? Before you actually apply an action, um, you can ask the human for confirmation. It's not clear that you really
Mhm.
want this in an agent, especially if you're running late and you're not looking at the time or you can't right now look, but maybe it's a better design, yes.
Uh,
Yeah. Nicole, you have other things you want to talk?
Sure. For second scenario, I think we can also place guardrails. For example, flagging which meetings can be moved.
Mm-hmm.
And also we can use the undoable action to allow users to revert a reschedule
Yeah.
immediately.
Yeah. For guardrails, how would you implement this? What would you look for? Do you have any ideas?
I think we can like give like give roles to like the members who are in this meeting. So we were talking about how like most people cannot decide when the meeting is, say if it's a client meeting. Uh,
Mm-hmm.
for example, the professional service team wouldn't have the privilege or the access to reschedule the meeting. Only the client can.
Yep. Right. So you might have some sort of rule-based system, right? Who has what permission and so on. Yep. All right. Sounds good. Yep. Go for it.
We talked about a guardrail for the meeting, like setting some sort of time limit before, so no action can be taken within 10 minutes or 5 minutes of the meeting.
Mm-hmm.
So it would be better to be 2 or 3 minutes late than sending an email to a bunch of investors asking to reschedule.
Maybe. Depends on the meeting, but yeah. I think that's a good idea. Anything else? All right. So what we talked about so far in the lecture was if you know that a certain mistake can happen, and you already know what the consequences are that you want to avoid, you can start thinking about how to design the system with guardrails and human in the loop and so on, that these problems don't occur. What I want to do in the rest of the lecture is talk about how do we know what we need to mitigate? And that's about anticipating risk, figuring out what the bad things are. So in a way, it's asking things, what's the worst that could happen? And I'm not usually worried about existential risk scenarios like this, but what's the worst that could happen for a train like this? You could certainly cause a lot of fatalities from a crash if it's going way too fast, if somebody's trapped in the door. And so you can think about a lot of these harms. Completely unstructured brainstorming is not necessarily the best way to think about this because there's all these biases of how people think about problems, and we would usually think about the things that come easily to mind, not necessarily about the corner cases and so on. So this is where better strategies often come in to think about what are the risks that we want to worry about so that we don't have to wait until the problem actually occurs, but can actually be somewhat proactive. This is known as hazard analysis. The hazard here are the bad things or the risky things that we want to analyze. Hazard in a formal setting is a dangerous state. It's not yet a problem, but it's a state where a problem can easily occur. And hazard analysis are strategies to proactively identify potential problems before they occur. Traditional safety engineering techniques, these have been mostly developed since the 1950s, often in a background from chemical plants, aviation. In a way, you will see in a minute, this feels very non-technical. It is essentially structured brainstorming, but the structuring will help to be a little bit more systematic here and capture a lot more corner cases that you may have overlooked otherwise. So let's start with one of these. And both the techniques that I want to show you are things that I want you to use in the next homework assignment too. STPA, System Theoretic Process Analysis, is a fairly modern hazard analysis process that's pretty involved. It typically thinks about entire systems. For example, if you have a human in the loop, how do you make sure that the human is well trained? Who checks that the human does the right thing? Who's managing that? And who's managing the managers? What are the incentives and so on? We're not going to use most of that because in most AI-based systems, there's not many controllers already there that we need to check very carefully. We're often much more worried about designing the system in the first place. So what we're going to use here are the first steps of the STPA process that are written on the stage. And they feel very straightforward, but I think going through them can be quite useful. The first step is identifying stakeholders, including indirect ones. Claire, I assume you talked about what stakeholders are?
I did near the end of class, but it was quick.
Does anybody remember what stakeholders are?
Anyone who has influence or is influenced by the project in mind.
Right. So it's a very broad definition. Everybody who has anything to do with a project, really. It can be the direct users. It can be people who are very indirectly associated with a project, like overseeing the project or not using the project, but still being affected by the project. So for the autonomous train system, can you just type into Slack a couple of stakeholders? We should be easily getting up to 30, 40 stakeholders here if we're just thinking about this for a moment. Passengers, yep. Conductors, or the lack thereof, right? we all fired them because we automate this away. The government oversight, the city who runs the train system, the transit authority, the owners of the train, yeah. People who use it in their daily commute, people who live next to the train tracks and might be affected by noise but not using it, engineers who repair the train, businesses in the city who benefit from passengers or not, landowners around the train stations. Yeah, I think you can see there's a lot of people who are there's a couple of stakeholders that are directly affected, taxpayers, and lots of people who are indirectly affected. And it's useful to have a list of those. Now, in the next step, what we're doing is for each stakeholder, we're trying to figure out what might they want from our system. So passengers, for example, want reliable transit at low cost. What's something that the government might want, or conductors, or landowners, or businesses nearby? No accidents. Noise control, right? Maybe trains should go around corners relatively slowly or quickly. On-time arrivals, no huge delays, low environmental impact, better wages for the conductors that we all fired, low maintenance, low operating costs, right, as an operator. Businesses want more traffic by their store, so they want maybe frequent good service. Right, so I think you get the point. Trying to go beyond the most obvious stakeholders here will help us think about what do other people who are directly or indirectly affected want from the system? What do taxpayers want? What does the government want from this? What do nearby business owners want? And the next step is essentially flipping those goals around and think about what are the risks here, or what are the bad outcomes where the stakeholders don't get what they want, right? What are the risks for each of them? Usually you can look at the goal or the value, like what do they want, and think about what kind of losses, what kind of damages, harms might they experience if they don't get what they want, right? This can be extreme things like loss of life and injury, where hazard analysis is traditionally done. It can be financial loss, loss of mission, but also loss of customer satisfaction, environmental loss, noise pollution, information leakage. And I think you can go through the list of stakeholders and their values and think about what are the losses here, right? So if we think about accidents, or no accidents as a goal, then accident is obviously a loss here, right? If noise control is a goal, then noise pollution is a problem. Low maintenance cost or low operating costs, then higher cost is obviously a loss here to those organizations. And now we can take these losses. We may have accumulated a list of 50 or 100 or more of these losses for dozens of stakeholders. And we can think about what requirements can we think about in our system to prevent it. And we're not really thinking at the level of specifications. It's really as requirements. What might we want from our system to prevent these losses? Can you give me a couple of examples of requirements that might come from goals that some of these stakeholders have, or some of these losses that they are worried about? So guardrails at the stations where passengers get on the train. So if you're thinking about, I want safety, I don't want to collide with a train, then you can think about how do we achieve this, right? What kind of requirements do we build? Screen doors might be one way. It might be a requirement that the operators might not like that much because screen doors are quite expensive initially. The train shall not depart until all doors are closed securely. The train shall arrive on schedule. Right? These are all reasonable requirements. Doesn't mean that we're keeping every one of these requirements, but by going through this process at scale, thinking about all kinds of stakeholders, indirect stakeholders too, and thinking about what do these people really want and what are they worried about. We can also talk to them. We don't only just need to think for them, but even just thinking about them might help. This gets us to a list of all kinds of requirements that we might consider. And some of them we might find kind of surprising or useful, and it may actually change us to design the system. Once we identify what the important requirements are, we can go through the process of thinking about how could the requirement be violated. We don't necessarily do this for every single requirement, but for the important ones, for the ones that we actually care about, for example, we want to reduce noise pollution. So we have a requirement that noise should not go above a certain limit or not at certain hours. We can start thinking about how might this be violated. And for that, the world versus machine discussions, assumptions, requirements versus specifications is actually a quite useful way to think about possible problems that could occur in the implementation that could lead to the bad outcome, to the losses that people are worried about. And so in a way, we can think about this. People living near the tracks have the value of peaceful living and good connections. Based on that, they're concerned about noise pollution. Based on that, we might think about a requirement to keep noise down to a certain minimum. And from there, we can think about what are all the cases, the causes of noise, and how can we actually reduce this in the system. So in a way, this feels super simple. And I think it is. The value really just comes from not just asking what's the worst that could happen, and then jumping just to the most obvious things, but to do this in a slightly more systematic way, to actually think about corner cases in a more proactive way before the problems occur. So I think we covered all of these. An example here, but in a way, it's really just structured brainstorming. It can be a lot of paperwork if you're required to do this in a very detailed way. If it's really a safety critical system, chemical plants, traditionally nuclear power plants, aviation systems, you might need to go through this process in a very structured way and produce a lot of paperwork. For most everyday machine learning systems, we're probably not going to be able to convince developers to do this. But I think doing this to some degree is better than not doing this at all. And maybe we don't need to do all the paperwork, but still think about, are there certain things that we have overlooked? It's quite controversial in the community whether you should use LLM assistance to this. What would be the arguments for using LLMs to help with this brainstorming and the arguments against? You have any thoughts? Could also raise your hand. Yep.
I guess for against like using LMs as brainstorming, I guess it could give you a false sense of confidence for I guess relatively important answers that
Yep.
I guess like if loss of life is involved, that's like very critical.
Yep. I think this is a common thing. You generate this, you might briefly look at it. It's a compliance check, right? You have done the analysis, and you may have not discovered a lot of corner cases because the model didn't do this. It could encourage laziness. It might hallucinate, might create a lot of extra effort. What are some arguments for using it? Or should we never use LLM?
It could provide a good starting point to begin with LLM. And from there, we can build upon the idea with the tribal and the traditional knowledge, and then we can propose something.
Yep. Can be a starting point, can help us in the initial steps. It can create a broader list of potential risks. So maybe if we did this manually, we would cut this off pretty quickly. For example, in traditional hazard analysis, there's advice to draw the system boundary pretty closely because otherwise it completely goes out of control. If you have 50 stakeholders, each of them has 5 values. For each of them, you can think of 3 losses. You have a huge number of potential requirements or losses, and you can't look at every single one of them. Another argument is cost. Developers don't really like requirements work. They don't really like this paperwork activity. So most of the time, unless you really force them to, they're not going to do this. You can force them if it's a medical device, if it's an aviation thing, because there's regulation. But I couldn't force you to do this when you're building some everyday software. If you're building transcription into a streaming website, if you're building your calendar agent, I don't think anybody would go through this process. I can tell you that you should do this in the class as much as I want. You're probably not going to do this, especially if it's very tedious and lots of paperwork. And the hope here is that maybe LLMs can lower the bar, that doing a little bit of this work with LLMs and finding maybe a few surprising results with very low effort is better than not doing this at all. And is maybe better, it's maybe incentivizing you to realize, oh, there's something that I forgot that I didn't see, and then spend more time looking closer. So in the next homework assignment, we want you to do some hazard analysis for a dashcam system that's described in the assignment. And then we also want you to implement this with LLM support. Right? So prompt an LLM so that you can actually scale this. So we want you to generate a report at a pretty large scale that you run mostly automatically, and then to look over this report and find 4 requirements that you thought were maybe interesting or surprising or important, and see whether that makes sense as a process of doing something lightweight, but then also looking over the results in a somewhat more critical way. There's other risk identification strategies, especially talking to experts is useful. And reading accident reports, if you're not the first product in an area, which you rarely are, right? Seeing what mistakes other people have made. But this kind of hazard analysis, the strategy, kind of structured brainstorming is a pretty useful strategy. Any questions so far? And once you have the hazards, you still need to judge which ones are you going to work on, which ones are you, where are you implementing safety requirements and mitigations into your system. We can't really help you to make that decision. Typically, you might want to look which of the discovered hazards is high priority because the risk is really, the damage is potentially very high and the probability is pretty high. But that's kind of engineering judgment and what risk level you're comfortable with. The other technique that I wanted to talk about is fault tree analysis. Fault tree analysis is complementary to hazard analysis. It tells you, I have a requirement here that's really important to me. How might I break this requirement? What may I oversee? So it's analyzing the possible causes of a loss. Hazard analysis gives you the possible losses, the list of possible losses of hazards or risks. And now what can go wrong that leads to the loss? Sometimes this is described as a forward analysis and a backward analysis, from the causes to the losses or from the losses to the causes. Fault tree analysis, again, feels very simple. It's kind of, you draw a diagram. It feels pretty straightforward, but again, the structured nature of this thing forces you to think through a problem in a somewhat structured way and look at often overlooked things. The way, let me explain this by an example here. The way that this works is that you start with a top event, which is a bad thing that you don't want to happen. So you have a requirement, and the top event is the violation of that requirement. In this very simple example here, it's no light is in the room, right? This is a bad thing that we don't want to happen. And then you think about backward, what are the things that can lead to this event happening? There are three possible causes in this diagram: that all the light bulbs are burned out, that the switch failed, and that there's a power outage, essentially. Some of these events you can, again, think about, why did this happen? Or when does the bad event happen? For example, there's a power outage because there's a power outage in the network, or your fuse was blown. So any of these things would cause a power outage, and a power outage causes a bad event that there's no light in the room. And then you also have end connections, which are interesting. So for end connections, both of the events need to happen at the same time for the bad event to happen, right? So for all lights to be burned out, both the first and the second light both need to be burned out at the same time. I guess I explained something very obvious in many words. This is essentially how fault tree analysis works. Start with a bad thing, and then try to think about what are the events that can lead to it. Here, the concept of specifications and assumptions is pretty useful because it tells you a lot of things that can go wrong. Especially assumptions are often overlooked in the system. The top level event is a violation of the requirement. So you start with the requirement, what you want. I want light in this room, so the violation is no light. But now you can think about what are the assumptions and what do you want the software to do. There's no software in this case, but I may have the implicit assumption that I never really questioned, that I don't have a power outage. So thinking about that is useful. And you can break it down often in many different ways. So let's take an example from the autonomous train. The requirement is we do not want to trap people between the doors. So using a fault tree, we can now identify possible problems that could lead to this. And we can think about, there's a requirement, and then there's a specification, the part that we implement with a model or without a model. And then we have a lot of assumptions around it, and we can question them one at a time. So here's a simple fault tree for this specific case. The top event is a person is trapped in the door. So the requirement was violated. So there you can think about what needs to happen for this bad event to occur. A person needs to be in the door and the door closes. Right? If only one of these things occurs at the time, it's fine. The person in the door, why is it there? I'm not sure that we really need to figure out why the person is there. We could figure this out, but I think we can stop there. But the door closes, we can try to figure out why did the door close when there was a person in the door. And we can think about multiple different reasons. Maybe the manual override was used. We have an assumption, maybe in the system, that the manual override is not used maliciously, but somebody could. Then a person in the door, the manual override was used to close the door. Somebody is trapped in the door. And maybe it's not worth to figure out the manual override. Maybe we just put on a penalty for abusing this and hope that this doesn't happen, and we ignore this and we're fine with the risk. But we can think about a person was not detected in the door. And why might this be the case? And we have maybe three causes here. The model made a mistake. This is a specification maybe that the model detects people in an image and just made a mistake. The camera was defective. We have implicitly an assumption that the camera gives us a good picture of the scene so that we actually have a chance in the pixels that the software sees to detect people, or the light conditions were poor. Maybe we had an assumption that we never questioned, that there's always well lit in the door area. When we see this broken down like this, we can start thinking about how can we make the system safer. You can look at the system, what's the minimal number of events right now that lead to the bad outcome. It's called minimal cut sets. I don't know that we need to go there necessarily, but what you can see here is that very few events will be sufficient for the bad thing to happen. If the model makes a mistake and a person is in the door, the bad thing can happen. That's sufficient, right? If the camera is defective, that's sufficient for the bad thing to happen. It seems pretty risky. We could try to put probabilities on these events. I don't know that that's super useful. I think the more useful strategy is to think about how can we make sure that the model is not a single point of failure. And so there are certain parts here that are probably unavoidable in general. We might be able to increase reliability, but it's still there and it's still a single point of failure. What we should do instead is think about mitigation strategies that need to independently fail. So here's the previous vision-based detector that fails, but we can introduce a door safety system, and these are connected with an end component. So this is the important part. The end component here shows that the model mistake alone can no longer cause a bad outcome. It means it needs to know. The problem now is that the model makes a mistake and the door system needs to fail at the same time. Only if these two events happen at the same time can the bad outcome happen. And so this is what you can see in a fault tree. And we can think about when does a door safety system happen, like a pressure sensor in the door, if the sensor fails or software crashes. It's a pretty stupid design where the software crash can lead to the door system to fail in a negative way where it closes the door. It's probably a bad default that we can fix. And the pressure sensor, maybe we don't want the pressure sensor alone to fail. Maybe we put in two pressure sensors, right? So this is the last update here where we put in two pressure sensors that need to fail independently for the bad thing to happen. And we get rid of somehow of the bad default. So if the software crashes, the door never closes. So the door safety system cannot fail in that way. What we've now done is that at least 3 events or 4 need to happen at the same time for the bad thing to happen. The person must be in the door. One of these for example, model mistake may happen, and both pressure sensors need to fail at the same time. This is way less likely than just the model making a mistake. And it's really useful to think about that many of these specific events happen to violations of assumptions. So it's really useful what Claire talked about in the last lecture to think about the assumptions, to think through the assumptions. What is in our requirements that we never speak about, but that we assume about the world to be true? And are they actually true? In the next homework assignment, we want you to do 1 or 2 of these diagrams for some events that you pick. Do you have any questions about this?
So I was wondering how, you said one of the advantage of human over LM is that we have more like common sense and assumptions, but since not everyone is an expert, so everybody has different assumption in the team. So
Okay.
I guess human can make wrong decisions. So how can we like make sure the people truly understand each other's assumptions?
So I think it's always useful to write down assumptions. I think it's often very boring to write down a very long list of assumptions. But writing them down, even asking an LLM to write them down, will help you to understand what am I actually trying to assume here, and are those assumptions realistic? And if multiple people write down their assumptions, you might find surprises about where different people assume different things. So that's maybe the closest I can think of here.
Okay, so like no specific framework, maybe just asking everyone to draw like their own version of this diagram will be very helpful.
Yeah, you could do this diagram, or you can do the assumption thing before then, right? You could just say, here's a requirement, or here's what I assume to be true about the world, so that it's sufficient. But yeah, this diagram will help you to think through this. If you can teach this to a number of people and can get them to actually draw this, or you let an LLM help with this and see which ones of these did you not expect. I think that's useful.
Okay, thank you.
Again, I don't think there's a single correct answer here. This is all a best effort approach. Can we anticipate a number of problems and design the system in a better way? Yeah.
Is this a better tool, or maybe I guess it could be applied in both scenarios, but say you're coming up with like you have an idea for a product or service, and this is kind of at the beginning, kind of outlining what we need to do and what we need to accomplish, or is it better used as an evaluation of we have this system, maybe it's not working as great as we thought. How can we adjust our approach?
You can use it for both. Typically, hazard analysis and fault tree analysis is intended as a design tool or requirements engineering tool, which you would do early, so that you already design the system. Retrofitting your train with pressure sensors is probably quite expensive. It's easier if you design this early on. But in practice, it can also be if you're realizing your system isn't working particularly well and you want to figure out why and improve it over time, you can use it in that setting too. You can use it to derive test cases later. So the typical advice is to do it early, but you can use it later.
Okay, thank you.
I don't know, Claire, whether you had different thoughts too.
Not really.
Okay. All right, go for it.
Yeah, in terms of the ML model mistake, Christian, if
Yep.
it's part of the spec as illustrated in this diagram, right? How do we take care of it? Like, can we have another ML model as a part of high availability, which can detect such mistakes and take some corrective actions?
So you can think about redundancy as a strategy. If you have two models and they both need to fail at the same time, it seems so you have two events that need to occur independently. If you have a safeguard here, which is a door safety system, potentially, you have this in here. You may see some isolation strategy in here. You might see a human in the loop where the human fails in relationship to the model. You can also just think about increasing the reliability of the model, make it more accurate, but it doesn't get rid of the fact that it's fundamentally a single point of failure. It might just make that failure less likely.
Okay, thank you.
All right. So I think this is a good way to try to wrap up. So fault tree analysis is certainly not complete. You can always break it down further. So at some point, you need to decide to stop. The whole point here is that you want to identify problems as early as possible, right? So identify stakeholders and identify what they care about. You can try, we haven't talked about those, but we can try to reason from component failures to hazards too. And you can try to reason from hazards to causes to think about how to make your design better. Again, these are all early phases, requirements, and design strategies. But it's this fundamental assumption that if you assume the model will make mistakes, right? The model is an unreliable component. You should probably think about what happens if those mistakes occur. How will they propagate? What requirements might they break? And what can we do to avoid this? So I'm pretty sure that most of you will not do hazard analysis in production, but I hope that some of you might. And to get you there, I'm forcing you to do this in the homework assignment. That's what I have for today. I'm going to stick around for questions if you have any. Otherwise, see you Wednesday, hopefully in person again.